To video lecture number 14 on linear equations. Now, these are not linear equations from algebra. These are linear differential equations. And in the previous lesson, we went over how to solve separable differential equations. And now we're going to learn about this new kind to recognize and the technique that you need in order to solve it. And this is just two kinds of differential equations. There's so many more. It's such a beautiful topic. So I hope you continue studying math and delve into it later. So definition. A first-order linear differential equation is one that can be written in the following form. So you have to put this to memory. dy dx plus p of x times y equals q of x, where both p and q are continuous functions of x on a given interval. So this is the standard. That's the form that you need to be able to rewrite your differential equation in for it to be considered a first-order linear differential equation. Let's start off nice and easy. We're going to just first determine whether or not the given differential equation is linear. So I have y prime plus cosine of y equals tangent of x. Let me rewrite this. This is dy dx plus cosine of y equals tangent of x. So let's see, does it match this form? There's dy dx. Do I have a function of x times y? No, I do not. I have a function of y. So already we have problems. And then is it equal to a function of x? Yes, but who cares, because already this term is not allowed. If we had cosine of x times y to the first, that would be fine. Notice it has to just be a plain old y, not a function of y. Just y to the first sitting there, hanging out, multiplied by whatever, some function of x. It could be crazy looking. So this is a no for this first guy. Okay, second one. X times y plus rad x equals e to the x times y prime. I'm going to rewrite this. Notice here, you need the derivative part isolated. This is isolated. And then on the right-hand side, there's only x's. Do you see that? And then if anything does have a y in it, it needs to be on the same side as the derivative. Okay, so let's rearrange and see where we're at. Don't automatically say, oh, b is no. Let's see. So I'm going to rewrite this as dy dx e to the x equals xy plus rad x. I want to get dy dx by itself, so I'm going to divide everyone by e to the x. So dy dx equals x over e to the x times y plus rad x over e to the x. And then remember, only x's are allowed on the right-hand side. So I'm going to rewrite this as dy dx minus x over e to the x times y equals rad x over e to the x. Oh my goodness, this is a yes. This is my p of x right here. Tricky, tricky. This is the q of x. Okay, so make sure you don't dismiss an equation right off the bat as not being linear, and also don't fall for some sneaky little trick thinking it is linear. In this section, they're all going to be linear, so don't worry, but later on down the road, when you're trying to identify whether or not you need to use the techniques for separable versus linear, versus maybe one day when you're in your differential equations class, you're going to know a bunch of other kinds of differential equations and their techniques. You want to be able to distinguish. Okay, so this is a yes. That being said, how do you solve it? Well, here are the steps. So first thing, write it in standard form. Standard form is when you have dy dx plus p of x times y equals q of x, like we did up above. Then you're going to find the integrating factor. I'll explain what that is in a hot second. I of x equals e raised to the integral of p of x dx. You're going to multiply both sides of the equation by the integrating factor. Then the left side of the equation should be I of x times y prime. Or I usually write it as d dx of I of x times y. If you want to know why, it's not magic. You can read the proof in your textbook or look it up online. And then from there, you just integrate both sides of the equation, solve for y. It falls into place so beautifully, really. One of my favorite kinds of differential equations. I hope you like them. So here we go. I got a few ready for us to solve. Solve the differential equation here. It's y prime equals x plus 5y. So first thing, I want to put it in the standard form and make sure that it's linear too. So I'm going to replace y prime with dy dx, and then I have minus 5y equals x. So yeah, that works. My p of x is negative 5. Make sure you put the negative on there. Oh my goodness, if you forget the negative, it can ruin the problem sometimes. So p of x is negative 5. Q of x is on the right-hand side, but nobody really cares about q of x. Sorry, q of x. And then let's get our integrating factor. So I of x is equal to e raised to the integral of p of x dx. That you have to put to memory. Why exactly it all works out this way is in the proof. Basically, you're making it a separable equation. So here we go. So we're going to have e raised to the integral of negative 5 dx. So if I anti-differentiate that, that's going to be e to the negative 5x. There's a plus c, but we just ignore it at this step. Because think of it like I of x, it's the integrating factor. It's just a tool to help you solve the differential equation. It's not actually part of the solution, if that makes any sense. So you don't need to worry about putting the plus c. I just want to get a function whose form is going to help me solve the differential equation. Okay, this is just a little tool that you're using. You don't show the tool in the answer. All right, once we get the integrating factor, what do? We multiply our entire differential equation by it. Okay, so everybody gets multiplied by e to the negative 5x. That means now I'm going to have dy dx times e to the negative 5x minus 5y times e to the negative 5x equals x times e to the negative 5x. You see that? And you might be thinking, my God, this looks a lot worse than it was when we first started. I don't know how I feel about this integrating factor. Just you wait. The left-hand side, provided you did everything right, should be the derivative with respect to x of the integrating factor, which is e to the negative 5x in this case, times y. You always need to check because this is where you can catch if you messed up. So check if this is true. Okay, so let's think here. We'd have to use the product rule, right? So say we left e to the negative 5x alone. Okay, there he is. And then I took the derivative of y, then it would be dy dx. Okay. Plus, now I'm going to differentiate e to the negative 5x. Well, I'd have to use the chain rule. So there's that negative 5, e to the negative 5x, and then I leave y alone. Yep, there it is. So it checks out. Beautiful. Equals x times e to the negative 5x. Well, now we're going to integrate both sides. So if I integrate the left-hand side, see how it's already the derivative with respect to x? That's just all going to undo each other. So all I'm going to have here is e to the negative 5x times y. And then now I will integrate the right-hand side with respect to x. Okay, so take a minute, make sure you understand. After you multiply through by the integrating factor, this is always going to be the integrating factor times y. Take the derivative with respect to x, double check it works, that it checks out, and then from there you integrate both sides. So all you're left with is I of x times y on the left, and then now we just have to integrate the right-hand side. So okay, how do we integrate x times e to the negative 5x? That's right, by parts. Oh, yay. So let's let u equal x. dv is going to be e to the negative 5x dx. So then du is dx. V would be negative 1/5 e to the negative 5x. All right, good. So that means we have here now on the right-hand side a negative 1/5 x e to the negative 5x plus 1/5 times the integral of e to the negative 5x dx. And then this is going to give us negative 1/5 x e to the negative 5x minus 1 over 25 e to the negative 5x. This plus c, yes, is necessary. It's part of my answer. And then remember here we've got e to the negative 5x times y. Okay, so how do I isolate y? Well, if I multiply both sides by e to the 5x, it'll cancel out on the left-hand side, e to the positive 5x, right? And just distribute that through. So then now I get y equals negative 1/5 x. That'll cancel out with the first term if I multiply e to the 5x with e to the negative 5x, right? So I just have negative 1/5 x minus 1 over 25 plus c e to the 5x. Now you can't replace that c e to the 5x with a k or something, right? Because that's changing like an exponential function, not just like some plus or minus arbitrary constant. So be careful when you go around. I know in the last section we replaced e to the c with k, but this is always a constant, so it was okay to do that. Here, this is behaving like an exponential function. You can't capture all that with a plus k. So I don't want you getting carried away with replacing things. Okay, good. Let's box this. Did you like it? I think it's so beautiful. So I hope you're enjoying this. These are fun. Maybe it'll inspire you to read the proof and see why the magic of the integrating factor works. Okay. Another differential equation, and you will need to remember, all your good integration techniques to solve a lot of these. So we have y prime plus y equals sine of e to the x. So let's see, dy dx plus y equals sine of e to the x. Yeah, this is linear. You don't see p of x, that's because it's just 1, okay? Yeah, p of x is 1, cool. So let's get our integrating factor, I of x. It's e raised to the integral of p of x dx. So it's e raised to the integral of 1 dx. So what's that? It's just e to the x. Okay, once you have the integrating factor, you multiply it by the original equation in standard form. So we have here e to the x dy dx plus e to the x times y equals e to the x times sine of e to the x. All right, now I have to check, this better be the derivative with respect to x of the integrating factor times y. What was the integrating factor? It was e to the x times y. And then here I have e to the x times sine of e to the x. So let's check that everything worked out. Okay. So derivative of e to the x we'll do later. Let's take the derivative of y. It's dy dx. We left it alone. Fabulous. Derivative of e to the x is e to the x. Leave y alone. Y. It works. Don't be lazy and skip this step, because a lot of the times if you mess up, you'll catch it right here before things get too late. Okay? Wonderful. So now let's go ahead and integrate both sides. So left-hand side's already a derivative. If I integrate it, it's just going to undo it. So all I have is e to the x times y equals the integral of e to the x times sine of e to the x dx. What do we do with the right-hand side? Can you tell? It's not bad. You could have done it back in the beginning of your calculus career. You just do a cute little u sub. That's right. So we're going to let u equal e to the x, and then du is e to the x dx. So that's going to be my du. Draw the kidney bean if it helps you. See how we got a cute little kidney bean there. All right, so this is going to be now sine of u du, and I still have that e to the x times y hanging out over there. So now I have e to the x times y equals negative cosine of u, which is just e to the x plus c. All right, almost done. So to get y by itself, I'm going to divide everyone by e to the x. So y equals negative cosine of e to the x over e to the x plus c over e to the x. Okay, that one was nice and not too terribly difficult to integrate, right? Okay, now we're going to look at some initial value problems where they're going to give us information so that we can actually figure out what c is. So first example, solve the initial value problem. We have t times dy dt plus 2y equals t cubed. They're telling me t is greater than 0, okay? And then y of 1 equals 0. So we'll save that for the end to find c. All right, I want to put it in standard form for linear equations. So remember, the derivative has to be isolated. dy dt has to be all by itself. So I'm going to divide through by t. So that means 2y is going to get divided by t also. So we have dy dt plus, let's write this as 2 over t times y equals t squared. So there's my p of t sitting right there staring at me. Hi, I'm p of t. I'm 2 over t. Okay, now let's get the integrating factor. So I of t is equal to e to the integral of 2 over t dt, which is equal to e raised to the 2 times the natural log of the absolute value of t. Now they told me in the problem t is greater than 0, so I don't have to worry about keeping those absolute value bars. And then I want to use my properties of logarithms here so I can simplify. So the 2 I can move to the exponent on t. And so e and natural log will cancel out, and I'm just left with t squared. Okay, so that's my integrating factor. What do I do with it? I multiply everyone in the original equation by the integrating factor. So let's do it. We've got dy dt times t squared plus, if I take 2 over t times t squared, one t is going to cancel, so I have 2t times y, and then a t to the 4th here on the right. Now this left-hand side better be d dt of I of t times y. Let's check. Let's check. Something didn't go awry. Okay, we're leaving this alone. Okay, derivative of y, dy dt. Now take the derivative of t squared. Yep, leave y alone. Looks good. All right, integrate both sides. Now we have t squared times y equals the integral of t to the 4th dt. Oh, this one's no big deal, nice and relaxing. So we have t squared times y equals 1/5 t to the 5th plus c. Okay, so that means y equals, if I divide by t squared, I have 1/5 t cubed plus c over t squared. Very nice. And then remember at the very beginning they told me y of 1 is equal to 0. So now I can find c. So 0 equals 1/5 times 1 plus c over 1. So that means c equals negative 1/5. So let's put it all together. Y equals 1/5 t cubed. I'll put minus 1, and then let's put the 5 with the t squared in the denominator. Oh, looks so good. Wow, wow, wow. Do you feel fancy? These are nice problems. Okay, I've got one more initial value problem for you, and then you can just do a bunch more with your homework assignment and have lots of fun. So solve the initial value problem, x squared plus 1 dy dx plus 3x times y minus 1 equals 0. So we have to put it in the standard form, and I do actually have to distribute this 3x because remember, you need a function of x on the other side, and you can only have p of x times y, not y minus 1 on the left-hand side. So x squared plus 1 dy dx plus 3xy is equal to 3x. Okay, things are looking up. Now let's divide by this x squared plus 1. So dy dx plus 3x over x squared plus 1 times y equals 3x over x squared plus 1. Okay, can you identify what p of x is? Yes, it's this whole expression right here, 3x over x squared plus 1. My goodness, okay. So let's go get I of x. I of x, you are e raised to the integral of 3x over x squared plus 1 dx. How do we anti-differentiate this? Do you remember how to use sub? We're going to let u equal x squared plus 1. So then du would be 2x dx. And now I have e. I'm going to take the 3 outside, so I'll have 3/2 integral of, that's right, du over u. Good. There's my x dx right here, and then I have a 3/2 sitting outside. Okay, so this is e to the 3/2 times the natural log of the absolute value of u, which remember, I can move that 3/2 to the exponent on the argument, and I have absolute value of u to the 3/2. Now what was u? U was x squared plus 1. Now think about it. X squared plus 1 cannot be negative. You're squaring a number, and then you're adding 1. So no, so we don't need to keep the absolute value bars. So I'm just going to write x squared plus 1 to the 3/2. There's our integrating factor at long last. We have found I of x. Okay. Once we have that, remember we multiply the whole equation in standard form by the integrating factor. So let's go. dy dx times x squared plus 1 to the 3/2 plus. Now notice I already have an x squared plus 1 to the first in the denominator. So that's going to cancel, and I'm just going to end up with x squared plus 1 to the 1/2 times 3xy. And then this equals, again, on the right-hand side, notice the x squared plus 1 is going to cancel. So I just have x squared plus 1 to the 1/2 power times 3x. All right, multiplying that throughout there. Now let's make sure this left-hand side better be the derivative with respect to x of I of x. So x squared plus 1 to the 3/2 times y. And then I'll just rewrite. The right-hand side is 3x times x squared plus 1 to the 1/2. Let's see. Is it true? Is it true? So I'm going to leave the integrating factor alone. Okay. And then take the derivative of y. Yes, I see it. Now, if I take the derivative of the integrating factor, I'm going to multiply by 3/2. And then by the chain rule, I need a 2x. So 3/2 and 2x cancel to 3x. And then there's x squared plus 1 only to the 1/2 now, and y left alone. Good. It checks. Voila. So now we can go ahead and integrate both sides. I just have x squared plus 1 to the 3/2 left here times y equals integral of 3x times x squared plus 1 to the 1/2 dx. So nice. Okay. How do we integrate the right-hand side? By using another substitution, right? Inside the radical, I mean, I didn't write the radical sign, but you know it is. It's to the 1/2 power. We have a quadratic function, and outside I have a linear function sitting there, so a little substitution works. Just don't use u. We already used u, guys. So let's let t equal x squared plus 1. So dt is 2x dx. Good. So we're going to have, let's take the 3/2 out again, integral t to the 1/2 dt. Very nice. So this is 3/2. If I anti-differentiate, I'm going to have t to the 3/2, but then I'm going to multiply by 2/3. So I'll just sub back in x squared plus 1 to the 3/2 plus c. Okay, let's put it all together. So left-hand side, we didn't forget about you. X squared plus 1 to the 3/2 times y equals, this is all canceled out. So I just have x squared plus 1 to the 3/2 plus c. Now I'm going to divide the whole equation by x squared plus 1 to the 3/2. And I get y equals, that's just going to be 1 plus c over x squared plus 1 to the 3/2. Do I box it? No, remember they told me y of 0 equals 2. Oh, okay, so let's go find c. So 2 equals 1 plus c over 0 plus 1 to the 3/2, which is 1. So I have c plus 1 is 2, which means c equals 1. Okay. So now I can say y is equal to 1 plus 1 over x squared plus 1 to the 3/2. And you can box that with pride. That was beautifully done. All right, so that's the end of the lesson on linear equations, in particular, not linear equations from algebra, no, linear differential equations. I hope you enjoyed it. Give it a thumbs up and subscribe, please, if you haven't already. And then after this, we're going to do sequences in series. How exciting.